Okay, so yesterday we filled in all the blanks for day 7. It's just 2 slides we're going to do, and again, this process is really the exact same as what we've been doing. The only difference is the context about what the mean is of. So this is not just, we're going to read example 1 here. We can tell what the context is because we have matched pairs. These are matched as a married couple. These are matched as a married couple. Again, the fact that it's talking about married couples tells us this is a matched pair. Versus I'm just looking at a bunch of random people and I take the average of something. I'm specifically talking about comparing each couple. And so what we need to do is, and we've done this once before, when it says, is there evidence that there is a difference in the ages of married couples? Just FYI, guys, this is a very common way to phrase the question. They will not say, run a hypothesis test or give a confidence interval. If they say, is this evidence, you have to do a hypothesis test or give a confidence interval depending on what the question is. And it's that way in your homework. So if you're ever confused on how to answer that, you give evidence by doing a hypothesis test. That's what we're going to do. So again, what we need to do here is we need to see the differences in their ages. We've done this before. I believe we've used this data table before. Let's go ahead and do husband minus, actually I lied because of the way it's laid up here. Let's go ahead and just do wife minus husband because of the way that it's labeled in the table. So we need to see what the differences are in these ages. So go ahead, take a second and just find all these differences, and then you can just put them right below the table right here. I'm gonna do the same. Okay, so we've got -6 here. We've got 3. We've got -10, 5, -6, -5, 9, -4, 23 minus 31, -8, -1, -1. Okay, so just because of the way that we had it set up, again, we have wife minus husband. So a negative age difference in this case means that the wife is younger, which, as you can see, is usually typical. It seems to happen that way for whatever reason. But again, even though we see differences here, on average, it could be that there is no difference. When we look at the average overall, it averages out. Some women are younger, some women are older, but it ends up averaging out, and there's actually no difference on average. So let's go ahead and work through the solutions. So here again, we're going to go ahead and do the null hypotheses and the alternative hypotheses. So I've got H null, H alternative. Again, we are talking about a mean here, but what's important to understand is that in a matched pair, we're talking about a mean difference. So when we have our null hypotheses, again, look back to the notes from yesterday. Null hypothesis is nothing is wrong. So if we're talking about a mean difference, the null is that there is no difference. That the average is 0. If I were to take the average of all these numbers, some numbers are negative, some numbers are positive, you can have an average of 0. Now, when it says that there is a difference, meaning that it's not 0. Otherwise, again, they would say something a lot about is the difference positive, is the difference negative, something like that. So this is just there is no difference, or there is a difference. And again, we want to identify where the claim is at. So that there is a difference. Where is our claim at then? Is that the null or is it the alternative? That there is a difference in the ages. That's going to be in the alternative, because if there is a difference, then the average difference is not 0. So there are our hypotheses. Okay, step 2, again, looking back to our notes, we need to choose the proper procedure. So our procedure, again, we're doing here, excuse my handwriting, I'm using my mouse, is again, it is going to be a t-test because we're talking about a mean, but specifically it is a matched pairs t-test. The mean we're talking about is an average difference between a pair. From there, let's go ahead and check your conditions. This should not take long. Now, with the conditions, again, the only difference with the conditions is that n specifically represents the number of pairs. So take a second and count there. How many pairs do we have? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so n equals 11. So this is our number of pairs. Now, because I want you to check the conditions yourself, but I want you to remember, we're talking about means here. Is that sample size big enough for normality? No. When we're talking about a mean, we need a sample size greater than or equal to 30, and that's not big enough. That's okay as long as this data is approximately normal. And when I say the data, we mean the data of the differences. So I want you to check your conditions. But again, when you check normality, you need to remember where to go in your calculator to get the NPP plot. Take a second, write your conditions. Okay, so for the conditions, we have random because it says SRS. Let's see independent. Again, apologizing for my mouse handwriting. We are going to assume the population is greater than or equal to 10 times 11, 110, right? Yeah, because there are more than 110 married couples in Arizona, right? This is our population. There's more than 110 married couples in Arizona. And then again, the normality, my sample size is not big enough. If the sample size was big enough, you just say, good, sample size is bigger than 30, we're good. But because the sample size is not big enough, we need to do an NPP plot. So you should have put in your differences. Let me go ahead and see this real quickly here. I got -6, 3, -10. I'm going to pull this over here for a second while I -6, 3, -10. No, just +10. Ah, dang it, -10. -5, -6. Things I get to delete out of the video. -5, 9. Oh my gosh, thank you. Good Lord, emulator is so irritating. -1, -1. Okay. Okay, so I have all my data in here. So again, we're going to NPP plot. I put all my data in. I'm going to graph, set. I've already got it set to NPP plot because we've been doing that. So I'll exit that out, graph 1. Okay, and that looks approximately linear, and so we say approximately normal. So we're good for that. Beginning to state that NPP is approximately linear. So it's approximately normal. Okay, there's our conditions. And once more, the only reason we had to do an NPP is because the n size was not big enough. If n is big enough, you're good. Okay, number 3, so here's where we get into the meat of it. So once you've checked your conditions, you need your test statistic and your p-value. Those are your next 2 things. Now again, with our test statistic formula, we know that for t, this is the formula we've been using for means. It's just that when you're doing matched pairs, the mean in the hypotheses will always be 0, and so that ends up going away. So when you're doing a matched pair, the formula does not change. It's just that it's going to become this because the mean from your hypothesis is 0. So take a second, find your t-value, keeping in mind that we have a list of data, and so in our list of data, we can get X bar and we can get S. So take a second. You need X bar from your list of data, S from your list of data, and then you plug it in. Okay, so going back to my data here, I'm going to go to the calculate section now because I need to calculate stuff. So my X bar, come on, there we go. X bar, I have negative 2.1818. So I'm going to write that down there. My X bar is negative 2.1818. And then my S is 5.844. Let's run that to 5. So I got 5.845. Yeah. There's my S divided by the square root of 11. So we go to our calculator. I'm going to do this on my actual calculator here, my hand, because I don't want to have to type this into that emulator because it's stupid. It takes me forever to type anything in. Let's see. Divided by 5.845 divided by square root 11. Oh, what did I do? Oh, that's right. Okay, so we should get a t-score of negative 1.2380. But yeah. Okay, so remember that the t-score is how you determine your bounds on your distribution. I highly recommend this, guys. If you have been skipping drawing your bell curve and shading your area, it's not technically required, but it's our visualization of our bounds that we need for TCD. Now, again, here is 0 right at the center. So where would the negative 1.238 go? To the left, right? Negative 2.38 is somewhere right here. So here's my t-score, and it's negative. Now let's look up to our, I just don't want to write negative 1.238. There's negative 1.238. Let's look up to our alternative hypothesis. So if I am looking at my alternative hypotheses, am I going to be shading to the left? Am I going to be shading to the right? Or am I doing a two-tailed test? Not equal to is a two-tailed test. So what that means is, even though this is the t-score for the value I'm looking at, I also technically want the absolute value on the other side of it as well. So let's review this. It's a t-score. So you are going to be using TCD in the calculator. When you use TCD, there are 3 things you need. When we are doing a two-tailed test, all you need to do is find the area of one tail and then double it. It doesn't matter which tail you choose because they are symmetrical. You just have to choose one. Typically, again, we choose the absolute value one. So even though my t-score was negative, typically we choose the positive of that, but it really does not matter. So again, you are going to be doubling your TCD. You're going to be doing one of these areas. Remember that it is lower bound, upper bound, and then degrees of freedom. This will give you your p-value. This is always step 3. What is your t-score? What is your p-value? Those go right back to back. Go ahead, take a second. What's your lower bound, upper bound, degrees of freedom? Choose one area and then double it. Let's see what we get. Okay, I am choosing to use the positive area. Again, it really does not matter, but that just makes my lower bound immediately my t-score. And I just like to do it that way. So my upper bound is my 1 with a bunch of zeros. You guys know the drill. My degrees of freedom should be, if my n is 11, my degrees of freedom is 10. So again, showing this where to go for this in the calculator. This is back out to the normal section of the calculator. We're going to option, stat, distribution, T. And there's TCD. Hey, there we go. I'm going to go ahead and bump it out to the front and add that 2 there. Okay. Careful you didn't forget the 2. Okay, so I have 1.238, comma, 1 with a bunch of zeros at the back end of it. That's fine. That's enough, honestly. Comma 10. Okay, 0.244. Okay, so my p-value is 0.2440. That would round to, that was 399, I believe. Yeah. Okay, so here is my p-value. Once you have your p-value, you're like, sweet, I'm at the end. The last step is to write your conclusion. So you've got p-value. You are comparing it to alpha. Take a second, look through. I just realized there. Why is that left off? Is this evidence there is difference in the ages of married couples? Let's go ahead and use an alpha of just 0.05 is typical. I left that off there. I'll just type that. Use an alpha of 0.05. Write this whole thing. So what I want you to do is, again, we need to say if we are going to reject or fail to reject, and then you need to say if that means there is evidence for the claim or not, and put it in context. We need to practice putting these things in context. Okay, p-value is 0.2440. I want it to be less than 0.05, but this is not true, so we fail to reject the null. What this means is there is not enough evidence that the null is wrong. If we cannot reject the null, there's not enough evidence it's wrong. And again, we want it to be wrong in this case because our claim is the alternative. So what this means is there is not enough evidence. Not enough evidence that so back up and read the paragraph, that there is a difference in the ages of married couples. That's the claim. There is not enough evidence that there is a difference in the ages of married couples. Let me erase that. Oh, I could have kept going. That there is a difference in the ages of married couples. So I know that looking at this, you're like, well, but look, every single one of these people had a difference in their ages. 0 did not occur at all. But you have to get out of looking at the data versus thinking about an average. Again, if there are negative numbers and positive numbers, for example, the average of -1 and +1, divide that by 2, this is 0. It's an average of 0. So even though overall, sometimes the wife is older, sometimes the husband is older, on average, it might balance itself out. So this sample has a very likely chance of occurring. This sample has a 24% chance of occurring if the average is actually 0. And so, okay, 24% chance of occurring, then probably the mean is 0, or at least we can't say it's not. So from here, guys, we have one more slide. One more slide. This last slide is just summarizing a couple things, because the last 2 lessons are just about errors that we can make with hypothesis testing, because we know there's a chance we're wrong. We've talked a lot about that. So we're just going to kind of summarize some things here. Okay, so the first kind of caution, and this is mostly important for when you're doing FRQ questions and they're asking you to kind of analyze things with hypothesis testing. The inference is not valid for all sets of data. Remember that we have certain conditions, right? So if there are outliers or bad data or bias inherent in the study itself, it doesn't matter if you can come to conclusion or not if there is some other bias affecting the results. So they might ask you to analyze a study, and even if you can come to some sort of conclusion, if somewhere else in this study you're like, that's going to lead to bias, well, then it's probably not going to be a valid conclusion. Remember, that's statistically significant. And if something is statistically significant, that means p-value less than alpha. So I'm going to say that right there, actually. Let's write that. We see this often. If something is statistically significant, that means that the p-value is less than alpha. That means we have evidence, and that's significant. But it does not mean practically significant. So for example here, it doesn't always mean practically significant. We can do all of the math, but in real life, it's not useful to us. For example here, I have a new SAT prep program. I tested 1,000 students, and their scores improved by a statistically significant average. Again, what that means is they did the math and figured out the p-value is less than alpha. By a statistically significant average of 5 points. Well, this improvement, this is just kind of knowledge that you guys don't know, which is why I'm just telling you. 5 points sounds great, but scores vary on the SAT test by 50 points. So to have an average of 5 points, change doesn't quite work out for us. It doesn't really help anything. You're like, great, it improved by 5 points, but the scores varied by 50 points. Just by like taking the test again, your score can change by plus or minus 50 points. So improvement by 5 points is not practically significant. Don't get married to alpha. Again, even though something can be statistically significant, there can be some other issues going on here. It says a patient is worried about high blood pressure and has measurement taken at random times during a week. The readings are all of these things. A reading above 140 is considered high blood pressure. Standard deviation is 5. Is this evidence at the 5% level that the patient has high blood pressure? I don't want to say this. Okay, we got... Can I type this? Oh my gosh, I'm stupid. 6? 1, 2, 3, 4, 5, 6. Okay, let's see. Graph. Okay, so again, on this example, this can happen, so you need to be careful. You may get through an entire problem and see that the p-value compared to the alpha level is a certain way, and you make a conclusion and you're good. Remember that even if you do all of this math, for example, in this math, what ends up happening is that the p-value, we're not going to do this whole thing, but the p-value is not less than alpha. And so we don't have enough evidence that they have high blood pressure. However, when you look at the data anyways, 145, 145, 150, 145, 150, even though the math says we don't have enough data or to say that they have high blood pressure, 5 of the 6 had high blood pressure. The reason why is you need to check your conditions. This sample is way too small. As well as that, not only is it way too small, but when you check the NPP, that is not approximately linear. So you have to be careful. It can happen where if conditions are not met, you can't do the test. If you come to a conclusion on the test, even if the conditions are not met, that's wrong. So be very careful to check your conditions, make sure that they're met. Because even if you think you've come to a conclusion, you're like, look, I did the math. I showed this. It doesn't matter because the conditions aren't met. Just because not less than alpha or less than alpha, the conditions have to be met. Again, on an FRQ, they might ask certain questions about this. If we perform 100 hypotheses tests at the 5% level on a set of data, how many should have significant results even if nothing unusual is going on. What this means is, and we're going to actually learn about this, the answer to this is 5 of them, 5% of them should get significant results. So meaning 5 tests. The reason why is, even if nothing unusual is going on, but we get a significant result that something unusual is going wrong, then we are wrong ourselves in our conclusion. We have a 5% chance of being wrong here. Do I want to actually even launch sample size? No, I lied. I'm gonna delete all this. Okay, so I went through this slide and then decided, actually, don't need this slide. These are kind of vague things to look out for. You're not going to see them very often. I don't want to say this. I got to delete all this. Okay, so actually I decided that we're going to go ahead and just not do that last slide. The tips on that slide are things that you should be doing anyways. Just reminders to check your conditions, reminders to think in terms of the context. And that, again, what we're going to learn in the last lesson, there is a chance that when you run a hypothesis test, you are actually wrong in your conclusion. And we're going to learn in the next lesson, what's the probability? We can actually figure out the probability of us being wrong on a hypothesis test. So we'll skip that last slide. You don't need it for the homework. From here, you're working on this assignment. Any other assignments that you are missing? We only have 2 lessons left. So you want to make sure you're all caught up for our test next week. Maybe next Monday, Tuesday. Okay, I will see you guys on Monday.